Lecture 35, Jacobians, Part 1. So Jacobian, let's start with a simple example of the one-dimensional problem. So we take an integration 1 to 2 integration 1 upon x dx. So after taking that the integral value of that integration, we obtain log x 1 to 2, we get log 2. Now if we understand the geometrical interpretation of that integration, so through the metrical interpretation we just taken a small strip, that is a function is 1 upon x, and we just taken a small strip here del x, and we integrate within that limit 1 to 2, means we just adding the small strips between the limit. Suppose if that is 1 and we are integrating 1 to 2, so we just adding the small strips. That is the geometrical interpretation of that particular integral. So but if we want to transform or change the variable in that integration, sometimes we are substitute using the substitution method. We substitute in that case, if we are substituting, or we can say transform x into the some new variable. So let's take 1 upon x taken as u, so we can say x is equal to u inverse or 1 upon u, and after taking the derivative del dx upon du, we write minus u power minus 2, and when we change the variable, so we also change the limit of that integration. So what we obtain here, the limit is 1 and minus plus 1 by 2, and on the 1 upon x we substitute u, and on the place of dx we write minus u power minus 2 du, or we can say du upon u square, or after integration we obtain the value same, that is log 2. So when we change the variable, that integration, what will happen? You see in that graph the function become that one. This the behavior of the function means del, in that case we are taking a strip, that is the strip, and if you see in the both cases the strips are entirely changed, means either the strip is stretched or the shape of that particular strip is changed if we transform, or we can say change the variable x into u. So here we have to notice that what we do, we are taking the integration a to b fx dx, and when we change the variable x into the u, so we get a function of f x of u, and on the place of dx dx upon du into du. So here that dx upon du, that one is called the first dimensional Jacobian. So this is what Jacobian means. This is the dx upon du is called one dimensional Jacobian. So here you have to notice that whenever you change the variable, it means you change the shape of the function, and Jacobian tell us how much the function is stretched, means you are changing the function, or you changing the shape of the function. And when you are changing the shape of the function, it means there the so as in the one dimensional Jacobian, similarly for the we can define for the two dimensional Jacobian. So if we consider one to one transformation from x y to uv, then x is taken as x of uv and y is taken y of u and v. So here, because we are talking about the two dimensional, so the integration fxy dx dy, that is area. So in on the place of that we write del x upon x comma y upon del uv, and this is what, this is the two dimensional Jacobian. And what is that? This is representing the region. So here r in the xy plane, and it map on the region r dash on uv plane. So here the Jacobian, Jacobian of the transformation is defined as del x y upon del uv. So we write an determinant del x upon del u, del x upon del v, del y upon del u, and del y upon del v. So we can also it written as the partial derivative of x with respect to u, partial derivative of x with respect to v, the partial derivative of y with respect to u, and the partial derivative of y with respect to v. And the determinant of that is called Jacobian of xy, or we can say the Jacobian. We can say when we say the Jacobian of xy, it means how much change when we change the variable x and y into uv. So how much change we obtain, that is tell us about by the Jacobian. So the geometrical concept of the Jacobian, if for xy plane into the r theta plane. So if we take a small area dx dy be the elementary area in xy plane, then the same element area in r theta plane is what? R d theta dr. So the area in xy plane is dx dy, and in r theta plane we write r theta dr. So why? Because if you are taking x is equal to r cos theta and y is equal to r sin theta, these are the polar coordinate. So the Jacobian of xy with respect to r theta, we write del xy upon del r theta, or the determinant of the partial derivative of x with respect to r, partial derivative of x with respect to theta, and similarly the partial derivative of y with respect to r and partial derivative of y with respect to theta, and we find the determinant of that. So the partial derivative of x with respect to r is what? Cos theta. The partial derivative of x with respect to theta we obtain r minus r sin theta, and the partial derivative of y with respect to r sin theta, and with respect to theta we obtain r cos theta, and after simplify that determinant we obtain r cos square theta plus sin square theta, and as we know the formula trigonometrical identity, we get r, and this is what? This is the Jacobian of xy. So the area is what? It means dx dy in the xy plane, and if we talk about in the r theta plane, so we write r d theta dr. It means that r is what? This is the Jacobian or del x y with respect to r theta, or we can say this is the Jacobian. So such concept may be extended for n variable also. If we are taking dx1, dx2, dx3, and we write the partial derivative, or we can say Jacobian of x1, x2, x3, and xn with respect to y1, y2, y3, yn into dy1, dy2, and so on dyn. So here this is what? This is the Jacobian of x1, x2, and so on xn with respect to y1, y2, yn. Means we are just if we are changing the n function of n dimensional plane, then we can write in that way. Now that is all about the Jacobian. Now in the simple way we can say Jacobian. If suppose u1, u2 be the function of two independent variables x1 and x2, then that determinant is called Jacobian of u1, u2 with respect to x1, x2, and this determinant is denoted by del of u1, u2 with respect to x1, x2. So you have always remember, if we write del u1, u2 in numerator and del x1, x2 in denominator, so you have to remember how we write the determinant u1, u2, u1, u2, and with respect to x1, x2, x1, x2. So this is Jacobian. Sometime we can also write just j u1 and u2. So this is mean the Jacobian of u1, u2 function, which have depend on two independent variables, which is there are two independent variable x1 and x2. In the similar way we can define for if we have a three function u1, u2, u3, and which is having the three independent variable x1, x2, x3, then we write the Jacobian, means the derivative partial derivative of u1, u2, u3 with respect to x1, x2, x3. So we write a determinant, you just write u1 with respect to x1, u2, u1 with respect to x2, u1 with respect to x3. Row wise, in the second row, u2, partial derivative of u2 with respect to x1, u2 with respect to x2, u2 with respect to x3, and the third row, partial derivative of u3 with respect to x1, x2, and x3. Or sometime we can write Jacobian u1, u2, u3. It means we are taking the partial derivative of u1, u2, u3 with respect to x1, x2, x3. And in the similar way, we can write this for the n dimensional n functions, which having the n independent variables. Now we take a simple example. Find the Jacobian of the following transformation. Suppose we have a function u is equal to ax plus by and v is equal to cx plus dy. So here we have to find the Jacobian of uv with respect to xy. So here we have given u is equal to ax plus by and v is equal to cx plus dy, that d is constant, that is dy. So now as we know, the Jacobian is what? Jacobian is, we have to find juv, means the del of uv with respect to del of xy. Here we are taking u and v is a function of x and y. X and y is a independent variable here. So what we do, we write the determinant del u with respect to x, del u with respect to y, del v with respect to x, del v with respect to y. So what we get, we take the partial derivative of u with respect to x. So u is that function. If you are taking the partial derivative of u, treating y as a constant, so we get a, and the partial derivative of u with respect to y, so what we get, b, and when we taking the partial derivative of v with respect to x, we get c, and the partial derivative with respect to y, we get d. And on solving that determinant, we get a d minus bc. So this is what, this is the Jacobian of uv, or we can say partial derivative of u v with respect to x y. We take one more example here. If suppose we have a function u1, u2, u3, which is a function of x1, x2, x3, then we have to show that the Jacobian of u1, u2, u3 is what, 4. So if you want to find the Jacobian of u1, u2, u3, so here u1, u2, u3 is a function of independent variable x1, x2, x3. So we have to evaluate Jacobian of u1, u2, u3. What it means the partial derivative of u1, u2, u3 with respect to x1, x2, x3. So we write the determinant, the partial derivative of u1 with respect to x1, u1 with respect to x2, u1 with respect to x3, and similarly u2 with respect to partial derivative of u2 with respect to x1, u2 with respect to x2, u2 with respect to x3, and similarly we write for u3, x1, u3 with respect to x2, the partial derivative of u3 with respect to x3, that is, and we get a 3 by 3 determinant. And now we take the partial derivative of u1 with respect to x1. So what we get, treating x2 and x3 as a constant, so we write minus x2 x3 upon x1 का x1 square. Then the partial derivative of u1 with respect to x2. So treating x3 and x1 as a constant. So the partial derivative of the x2 is 1. So we get x3 upon x1. Similarly, x2 upon x1 with respect to x3. And now in similar way, we take the partial derivative of u2 with respect to x1, x2, x3. So we get x3 upon x2, x1 upon x3 into x2 square, x1 upon x2, x2 upon x3, x1 upon x3, and the partial derivative of with respect to x3, we get minus x1 x2 upon x3 square. So we get the determinant. Now you simplify that determinant, so you just take common 1 upon x square in the first row, and second row we get minus x square, x2 square, and third row x3 square. So what we get, 1 upon x1 square, x2 square, x3 square, and we get minus x2 x3. Here we get x3 x1 x2 x1, and the similar way we get x3 x2 x1 x3 x1 x2 x2 x3 x3 x1 and x1 x2. Now you apply the row operation on r2 plus, if we take r2 plus r1, so we get, this is the common term, x1 x2 square and x3 square. We get x2 x3, the first row is same, and this becomes 0 0, and we get 2 time of x1 x2. The third row is again same. Now apply the operation on third row, r3. We can also apply r3 plus r1. So what we get, x2 x3 x3 x1 x2 x1 0 0 x1 x2, that's become 0, and this become 2 time of x1 x3, and this become 0. And also we have common value x1 square, x2 square, x3 square. Now after expanding that determinant, we get this into that one, that is 4 time of x1 square x2 x3, and multiply that term, we get 4 x1 square x2 square x3 square. We get a negative sign, negative negative, we get positive sign. Now if x1 square x2 square x3 square cancel out, and we get obtain the value 4. So this is the value of Jacobian. This is what j of u1 u2 u3. So in that way we can show that, or we can find out the Jacobian if we have a function, different functions.